Hey, Science 30s, and welcome to our second discussion about topic 2.1 in Unit D, harvesting nuclear energy. Last day I introduced you to nuclear chemistry and how you can balance out various types of nuclear radioactive decay reactions, whether they're alpha decay, beta decay, or gamma decay. Today I want to take the topic of nuclear energy to its conclusion, which would be how do we harvest these types of nuclear reactions to actually create electrical power, and why do these reactions generate so much electrical power? So to start off with, the radioactive the radioactive decay reactions I talked about last day. Some of them can be very damaging to human tissue, uh, specifically the gamma decay reactions. But these types of decay reactions do not generate enough energy to basically create the amount of electricity that humans are basically looking to produce to power cities and industry and homes in large areas. What we need for that is we need another type of a nuclear reaction known as a nuclear fission reaction, where we physically actually rip isotopes apart. So we take one isotope and basically split it into two other isotopes, basically ripping the atom, for lack of a better term, ripping the atom in half and releasing energy as part of it. Because these strong nuclear forces that hold these atoms together, if we can break those forces, that's going to release huge amounts of energy for us. Now, the nuclear fission reaction, as I mentioned, or you're basically looking at one isotope that's going to split into two. A very common one of these reactions that's used in nuclear reactors, even here in Canada, which I'll get to in a couple seconds, is the fission reaction of uranium 236. If I take uranium 236 and basically bombard it with high energy neutrons, I can basically break it into barium 141 and krypton 92, and I can release several more neutrons, which I'll get to their importance in a couple of seconds. Now, as I mentioned, this reaction, as it stands right here, is the one that powers nuclear power plants in Ontario, which are known as CANDU reactors. CANDU reactor stands for Canadian Deuterium Uranium Nuclear Reactors, and these are found, as I mentioned, in Ontario. What they're going to do is they're going to do a series of energy transformations using the laws of thermodynamics, right? We cannot destroy or create energy. We can only take energy and make it transfer forms. So we're going to take the intranuclear potential energy of the uranium atom or isotope. When we split it open, that's going to cause a release of energy, which is going to convert into thermal energy. That heat energy is then going to power the boiling of water. We're going to boil water, and then that water, when it boils, is going to release steam. And that steam is then going to, in turn, create the kinetic energy that's going to turn turbines inside the reactor. These turbines are then connected with shafts that basically connect into generators. And if we create motion inside of a static magnetic field, which is generated by the permanent magnet inside of a generator, we can create a secondary, essentially an electromagnet inside of the generator, which will then create essentially a magnetic energy or a magnetic field, and that magnetic field will then create the electrical field or the electrical energy, which can then be released out of the generator and then sent down, through high voltage lines and transformers, as we talked about in the Unit C, and then that energy can be sent to homes. It sounds very similar to the process that I talked about with coal-fired power plants earlier in the unit, and it is, because pretty much we're doing everything that those coal-fired power plants did. The only thing that's different is we're using this intranuclear potential energy rather than the combustion reaction of burning the coal to basically create our thermal energy. If you want to see how one of these reactors works, watch this video here. I'll give you a quick little run through of how a CANDU reactor or a nuclear power plant actually does its thing. Now, as I mentioned earlier, the reaction does generate these extra neutrons. Now, these extra neutrons are basically going to want to collide with other atoms of uranium, which will then set them off and cause them to actually want to break apart and undergo fission reactions as well. The problem with this is we have to be able to control the release of these neutrons. If we let too many of these neutrons get reacting with too many of these uranium-236 isotopes in too short of a time, you can get essentially an out-of-control chain reaction, which could eventually lead to a potential meltdown, a nuclear meltdown you may have heard of, which is what happened in Chernobyl in the Ukraine, then the Soviet Union, now in the present-day Ukraine, and that was because they weren't able to maintain or keep that chain reaction under control. If you want to see other than Chernobyl, because there are a lot of radioactive places on Earth, if you want to see, actually, I'm going to skip that one. That one you can find on my website. If you want to see the most dangerously radioactive places on Earth, go to my website. There is a link there for it as well. You know what? I can't throw it in here because I can only put 5 links in my video, so I'm kind of stretched with my links today. What I will show you, though, instead, but if you want to see that video, go to my website about the most radioactive places on Earth. But if you want this video, I want to show you instead is going to be about the radioactive byproducts of these nuclear energy and these reactions. Where do we store this material? How do we keep this radioactive material once we break these atoms apart? We're creating unstable isotopes that want to undergo radioactive decay and release gamma radiation. Where do we store that? Where do we keep that stuff? Watch this video to find out, and it will talk you through how we actually store it. And there's a lot of, in Ontario right now, there's a community that just basically signed a deal with the Ontario government to basically become a deep underground storage site of radioactive waste directly below their town, about a kilometer below the surface. Is going to be a dumping site for all this material that's going to be stored in these underground caverns that are basically that's where they're storing it. But different places of the world have different solutions to how they're storing this radioactive waste. But it is an issue because the more nuclear energy we produce, the more radioactive waste we're creating, and we have to find a way to safely store that as it continues to break down and release deadly forms of radiation that would be deadly to life on Earth or to humans or pretty much any form of life on Earth. So watch that video if you're interested. So how do we control these chain reactions in a reactor? How do we stop it from going Chernobyl? How do we stop a reactor from going Chernobyl? Well, what we use something called heavy water. And the CANDU reactors are something called heavy water. Now, what is heavy water? It's not a water that likes Iron Maiden or Judas Priest or heavy metal. It's basically heavy water because it weighs more than regular water, because it uses an isotope of hydrogen. It uses the hydrogen-2, which is a little bit heavier than regular hydrogen, which would be hydrogen-1, essentially a single proton. This is hydrogen that has a neutron as well as a proton in it. So this is called deuterium. Deuterium is the form of hydrogen, or the isotope of hydrogen that's used in heavy water. And it basically creates a situation where these neutrons can be sort of contained. They basically slow the speed of the neutrons down, and it's ideal for this fission reaction of uranium. Due to its role, heavy water is referred to as a moderator because it slows the reaction down. How can we make nuclear energy safer and or cleaner? Before I move on, take a watch of this video to see how we can maybe change some of the things we're doing with nuclear energy to make it a little bit safer to use. That maybe more countries may jump on this form of energy, which is still highly controversial, but may be a possible solution to some of the energy crisis that we are experiencing in parts of the world. So just to give you an idea, a small pellet of uranium has a mass of roughly 7 grams. So a very small pellet. This is a very small amount of uranium that's used in these reactors. But it can release the same amount of energy as roughly 556 liters of oil, or 500,000 liters of natural gas, or 807 kilograms of coal. How is this possible? How can this occur? Well, the reason why is it's not necessarily the mass of the substance, it's actually the sum of all of its parts. In this case, it's the protons, the neutrons, the electrons that are all playing a role in the creation of the energy. You must and again, this was the reaction, or I guess the formula that Einstein came up with, and it's a very famous formula that he came up to calculate. How can we calculate amounts of energy that are produced by very small substances, and how can they release that amount of energy? If you're interested in knowing what Einstein proposed, take a watch of this video. It's going to give you a short little introduction to Einstein and that famous equation of his and how he got it. But basically, the equation states this: it's E equals mc squared, or delta E equals delta mc squared. And basically, the reason why we're producing so much energy is it has to do with essentially the fact that C is a massive value. We're releasing photons of energy as part of this release of energy, and those photons are being released at the speed of light, right? So what you've got in this equation is you've got delta E, which is your change in energy, represented in joules. You've got C squared, which would be C would be the speed of light, which would be 3.00 times 10 to the 8th meters per second, as we talked about in unit C, and the second half of unit C under the electromagnetic energy portion of the unit, the electromagnetic spectrum. And then we also have a change in mass. There is going to be a change in the mass of these isotopes in one of these fission reactions, and we're going to measure that change in mass in kilograms. So and again, I'm going to read this off the slide, just particularly due to the fact that the square of light speed is incredibly large, and a small change in mass can correspond to a very large. You can get a very small change in mass that will correspond to a very large change in energy, because you're dealing with this massive number of 3.00 times 10 to the 8th. That's how these very small amounts of uranium or plutonium or whatever you're using to basically generate these reactions, that they can produce massive quantities of energy because of that factor. You're factoring in the speed of light with the release of some of the particles that are being released out of these nuclear reactions. So how do we calculate? The biggest thing about these reactions is the toughest thing is this. The toughest thing is, how do you calculate the change in mass? How do you calculate the change in mass between an isotope of uranium to, let's say, krypton or whatever? How do you do that? Well, we use a method very similar to what we discussed earlier in the unit when we talked about Hess's law. We talked about how we can calculate the changes in enthalpy with Hess's law. Well, what we're going to do is we're going to use changes in mass between the reactants and the products to basically calculate, whether the reaction is endo or exothermic, and what the overall change is. And the good news is, again, you don't have to memorize it. In this case, you're going to be dealing with a set of masses that are provided for you in the data booklet on page number 8, masses of selected nuclides. That is going to be the key to these equations using Einstein's equation. Is Einstein's equation here? Yes, Einstein's equation. If you forget it, it is down there as well, and it tells you what everything is related to on the equation. So don't panic about that. Everything you need to know is on page 8 of your data booklet when it comes to these calculations for E equals mc squared. Let's run through an example where we're actually given the change in mass. Let's start off with an easy one. This one isn't up on the board. I'm going to give you a tougher one on the board, but the easy one is just on the notes slide right here. So I've got a fission reaction of 1 mole of beryllium-8. The mass of the products is going to be 2.29 times 10 to the negative 5th kilograms less than the mass of the reactant. So we're going to have less product than reactant. Calculate the change in energy and whether the reaction is endo or exothermic. All right, well, let's plug this into our equation. Do we have our mass change? Yes, we have a delta M value here. We have, in this case, it's going to be negative 2.29 times 10 to the negative 5th kilograms, because we have less, the mass of the products is less than the mass of the reactants. And we also have a C value. We always know C. It's going to be 3.00 times 10 to the 8th. So if I take those two values and I can basically plug them together. Now in the equation here, it doesn't put a negative value on it, but I will give you a quick clue on how whether or not it's endo or exothermic in a second. So basically, if I take my 2.29 times 10 to the negative 5th kilograms times 3.0 times 10 to the 8th, and I square that value, I'm going to get a value of 2.06 times 10 to the 12 kilograms times meters squared divided by seconds squared, which is essentially a fancy way of saying a joule. So the answer for this question is going to be 2.06 times 10 to the 12 joules is going to be my change in energy. Now the question is it exo or endothermic? Here's how you calculate that. The fact that products, in this case, weigh less than the reactants indicates that energy is being released. So if we get a drop in mass, it's an exothermic reaction. If there is an increase in mass in one of these nuclear reactions, it's going to be an endothermic reaction. But let's be honest, a nuclear fission reaction, a nuclear fusion reaction, all of these are pretty much going to be exothermic reactions, because why would we use them if they're endothermic reactions? We wouldn't be able to generate energy. We would be sucking energy into the reactions. So it kind of goes without saying that these are all going to be exothermic, but the best way to determine whether it's exo or endothermic is whether the products weigh more or less than the reactants. If the products weigh more, then it's an endothermic reaction. If the products weigh less, then it's an exothermic reaction. Now, this was an easy question because they pretty much gave you your delta M value, and they gave you, well, you already knew C. So this is a very easy question to figure out. But what happens if they give you an actual equation? What if they actually give you an equation that is basically telling you, all right, I want you to calculate delta E, and I'm just giving you an equation written on a board? Then it gets trickier. At that point, you got to switch to page 8, and you've got to start looking at each of the elements or all the isotopes that are in the equation, and you have to calculate the mass of each of them. So what we're going to do is we're going to calculate the total mass of this side of the reaction, of my reactants, and I'm going to calculate the total mass of my product side, and I'm going to subtract the two from one another, and then that will be my delta M value. Then I can then multiply that with my C squared value to get my delta E value. So let's run through this really quickly. It's up on this slide right here. I'm going to walk you through it sort of step by step here as we go along. So right now, the first thing is to determine the mass of the reactants. So I'm going to go on to my data sheet here, and I'm going to see that I've got uranium-235. It gives me a mass of 235.04392, and that's kilograms per mole. Well, there's only 1 mole of uranium because my coefficient technically is 1. So I'm going to have a mass of 235.04392 kilograms for that 1 mole of uranium. Then I've got to figure out my neutrons. My neutron masses are going to be on the top of the page. So there's my mass of my neutron. It's going to be 1.00866 times 10 to the negative. So, and I apologize for that. I'm not reading that properly off my thing. Each of these values is going to be to the 10 to the negative third. Sorry about that. I didn't read that very carefully on the sheet there. But so in this case, if you look on my slide here, and if you've got the slides up at home, I would maybe pull the slide up right now. Very difficult to see it on this slide, but if you can grab my notes right now, it's all there. So basically, I'm going to have 1 mole of times 1 mole of uranium will be 235.04392 times 10 to the negative third kilograms per mole. I've got 1 mole of neutrons, which will be 1.00866 times 10 to the negative third kilograms per mole. If I add those together and multiply the moles and cancel out the moles, I'm going to wind up with 236.05258 times 10 to the negative third kilograms. That value that's there, which is going to be, I'm going to write it up on the board here. This would be the combined mass here. So this would be 236.05. Tough for me to read it off of here. Sorry, guys. Times 10 to the negative third kilograms. So that's my mass of my reactants. Now I'm going to go to the other side. I'm going to figure out my barium 141, my krypton 92, and my 3 neutrons. Again, if I calculate my mass of my products and I run through my data sheet, all the information is there. It's up on my slide there. If I calculate all that information together, I'm going to get a value for this side of my mass on this side is going to be 235.866 times 10 to the negative third kilograms. So I can see immediately that the weight of my reactants is more than the weight of my products. I've lost mass. I know it's an exothermic reaction. That's not going to be an issue. So what I can do now, though, is I take this number and this number. I'm going to subtract the two from each other. So I'm going to determine the change in mass by doing my delta M, which would be my M of my reactants subtracted from the M of my products. That's going to give me, if I subtract these two from one another, I'm going to get a value of 0.1868 times 10 to the negative third kilograms. That's my delta M value. Now that I've got my delta M value, I can plug that into my E equals mc squared equation. I can take delta M times it by 3.00 times 10 to the 8th squared, which is going to give me a value now of, when I've calculated all of that together, I'm going to wind up with a value for my delta E of 1.67 times 10 to the 13th joules. That's my delta E, and that is for every mole of uranium-235. So that's per mole of uranium-235. That's basically what we're releasing with every mole. Again, to calculate the delta M value, you need this data sheet on page 8. That's all your masses per mole, kilograms per mole, of each of your radioactive or your possible radioactive isotopes that you would see in the equation. So that's your sort of your really tough math component. Actually, that's probably the toughest math component I think that's left. I don't think there's a lot of really tough math coming up after this one. This is sort of the last kick at the math can before the end of the year. But that, you're going to pretty much going to see an equation where I'm going to ask you to calculate a delta E value for sure, and the government would definitely throw one potentially at you as well. To finish up today's discussion and our discussion of 1.4, there is one other type of nuclear reaction that is sort of gaining a lot of interest out there with scientists, and that is the nuclear fusion reaction. Nuclear fission reactions break isotopes apart. Fusion reaction is all about putting isotopes together. The most famous fusion reaction is the one that powers the sun. That's going to be hydrogen 2, so deuterium plus deuterium, essentially, or the heavier isotope of hydrogen. If I put two of those together, I'm going to get helium. That I don't think is right. That is not right. I see a typo on my slide there. I knew that was wrong. You're going to get helium-3, and you're going to get the formation of a neutron, and that's going to release an incredibly large amount of energy. And this is obviously it is a form of renewable energy. As I didn't really mention that, but nuclear fission reactions are considered to be non-renewable energy sources because once we use that uranium, we basically spend it. Hydrogen is the most common element in the universe, so we consider the use of hydrogen in a fusion reaction, if we could ever get one to work, that would be a form of a renewable energy. So just the difference. Fission reactions are considered to be non-renewable. Fusion reactions are considered to be renewable. So anyways, in this case, this is providing a lot of energy. How much energy are we talking about? The sun, 1 gram of the sun, can produce roughly 339 gigajoules of energy. That is the same as roughly 9,000 liters of oil. And to put that in perspective, the sun has a mass of 2.0 times 10 to the 33rd grams. So there's a lot of energy that sun is producing. And if you factor in to the equation that the sun, the energy from the sun, we only get about 1/2 billionth of the energy of the sun that actually hits the earth at any given time of the day. That basically is the equivalent of 4.3 times 10 to the 19th joules of energy provided by the sun every hour. So there's a lot of interest. This is obviously why we would like to look at solar energy, but this is something different. Could we reproduce a fusion reaction on Earth and use that as a power source? We have not been able to do it yet because there's a lot of limitations on what we are able to do at this time because technologically, I guess we're just not there yet. But if we could ever somehow reproduce this reaction and be able to control it, it would be essentially an unlimited supply of energy. How come humans don't use it directly as an energy source yet? Here's the video. Give this sucker a watch, and that'll give you a couple of reasons why right now we're just maybe not ready for fusion reactions. But at some point in the future, hopefully we might be able to tackle that one, and we might be able to solve the world's energy problems and pretty much put every other type of energy out of business and just fuse our energy together and basically make it happen that way. That's it. That's our topic for 4.1. Before I give you your homework, which will be at any second now, here's a recap of what we discussed today. Give that a shot and just make sure you're all comfortable with the concepts that were covered between today and, in fact, the even parts of the last lesson, our part 1 discussion on 4.1. Homework is now going to be covering the last 2 videos, both the videos for 4.1. Here are the questions I'd like you to do. Questions 26 to 36 and questions 38 to 41 on pages 503 to 517, and questions 2 to 8 on page 519 in your Science 30 textbook are due for next day. That is our conversation. We are now done the first half of Unit D. We're in the home stretch, folks. 2 more videos coming your way. We'll be discussing the second half of the unit starting next time. We've got 2 videos left to finish up the course. Actually, we'll be discussing Unit D, Chapter 2 next day, the start of that, which is called Dreams of a Sustainable Future. We'll be discussing all sorts of renewable energy sources that are available to us right now because we don't have fusion reactions yet available. So what can we do to use as other forms of renewable energy? That will be my discussion for the next couple of lessons. Thanks for tuning in, everybody, and we will see you very soon.